Fusion energy has been called the holy grail of power for decades. Since the 1950s, scientists and politicians have promised that within just 20 years, humanity would have working fusion reactors providing limitless, clean, safe electricity. Yet those 20 years kept slipping away, always out of reach. More than half a century later, we still don't have a commercial fusion power plant. But that doesn't mean fusion is a fantasy. It is instead one of the most ambitious and difficult scientific and engineering projects ever attempted. The truth lies somewhere in between the promises and the breakthroughs. Real, measurable progress on one hand, and still unsolved, massive challenges on the other. To understand why fusion energy is so attractive, just look up at the sky. Every star shines because of fusion. In the cores of stars, lightweight hydrogen nuclei collide and fuse into helium, releasing immense amounts of energy in the process. Our sun has been doing this for billions of years, and it will continue to do so for billions more. If we could reproduce that process on Earth, it would mean practically limitless fuel, no carbon emissions, and almost no long-lived radioactive waste. The fuel, deuterium and tritium, can be extracted from seawater and lithium. The risks of runaway chain reactions, meltdowns, or disasters like Chernobyl or Fukushima are virtually non-existent because fusion is inherently difficult to sustain. If something goes wrong, the plasma simply cools and the reaction stops. But creating fusion on Earth is far harder than it sounds. The sun has gravity on its side. Its immense mass compresses hydrogen nuclei together. On Earth, we need to mimic those conditions artificially. To overcome the repulsion of positively charged nuclei, they must be accelerated to incredible speeds by heating them to over 100 million degrees Celsius. At those temperatures, atoms strip apart into plasma, a state of matter where nuclei and electrons move freely. Containing such plasma is like trying to bottle a star. And that is where humanity has been struggling for decades. Two main approaches dominate the field today: magnetic confinement and inertial confinement. In magnetic confinement, plasma is trapped in a donut-shaped chamber and held in place by extremely powerful magnetic fields. This is the principle behind tokamaks and stellarators. In inertial confinement, tiny fuel pellets are bombarded by lasers or particle beams, compressing them so quickly and violently that fusion occurs inside for a split second. The tokamak, invented in the Soviet Union in the 1950s, has become the main path for research. A tokamak is shaped like a torus, a giant ring. Current driven through the plasma itself, combined with external magnetic coils, creates fields that keep the plasma away from the chamber walls. If the plasma touched the walls, it would instantly cool and collapse. Today, the largest operating tokamak in Europe is JET, the Joint European Torus in the UK. In 2022, JET achieved a record, more than 59 megajoules of fusion energy released over just a few seconds. That's still far from powering a city, but it's an undeniable milestone. The next big step is ITER, the International Thermonuclear Experimental Reactor. Being built in southern France, ITER is the largest scientific project in energy history. It is a collaboration between the European Union, China, India, the United States, Russia, Japan, and Korea. ITER is designed to demonstrate that fusion can produce more energy than it consumes, a threshold known as net energy gain, or QNGT, 1. If ITER succeeds, it will be the closest humanity has come to showing that fusion power is truly possible. First experiments are expected in the coming years, with full operations around the 2030s. Stellarators take a different approach. Instead of using plasma current to help shape the magnetic field, they rely entirely on intricate, twisted external magnets to keep the plasma stable. They are harder to design and build, but they avoid many of the instabilities that plague tokamaks. The most advanced stellarator is Germany's Wendelstein 7X. In recent years, it has shown that plasma can be stably maintained for tens of minutes, a major achievement. Inertial confinement, meanwhile, is pursued at facilities like the National Ignition Facility, NIF, in the United States. At NIF, nearly 200 of the world's most powerful lasers are focused onto a tiny capsule containing deuterium and tritium fuel. The outer layer explodes outward, and the inner core is crushed inward at incredible speed and pressure. In 2022, NIF scientists announced a historic breakthrough. For the first time, the energy released by the fuel itself exceeded the energy absorbed by it. It was a symbolic ignition moment, showing that fusion fuel can actually deliver a net energy release. But overall, the lasers consumed far more electricity than the reaction produced, meaning the facility as a whole still had a strongly negative energy balance. So what do we really know how to do? We know how to create plasma at temperatures of more than 100 million degrees. We know how to keep it confined for seconds or even minutes without collapse. We know how to trigger fusion reactions that release energy and produce telltale neutrons. We know how to design superconducting magnets that are stronger and more compact than before, using new high-temperature superconductors. We've proven in the lab that fusion can release more energy from the fuel than is absorbed. What do we not know yet? We still don't know how to build a reactor that produces more total energy than the entire system consumes. We don't know how to run a stable, continuous fusion reaction for hours or days. We don't know how to breed and recycle tritium efficiently enough to sustain power plants. We don't yet have materials that can withstand decades of intense neutron bombardment. And we haven't found a way to make a fusion plant economically competitive with today's energy sources. Why then do promises keep coming? Because every real milestone is progress, even if the finish line keeps moving. ITER will test net energy gain. Wendelstein 7X proves stability is possible. NIF showed ignition in the lab. Meanwhile, private companies are entering the race. Startups in the US, UK, Canada, and China are raising billions of dollars, claiming they can commercialize fusion sooner than government megaprojects. They experiment with compact devices, high-temperature superconducting magnets, more efficient lasers, and hybrid concepts. Some boldly promise working reactors in the 2030s. Whether these promises hold is unclear. History warns us to be cautious. But the influx of private innovation is undeniable. The potential of fusion is enormous. Deuterium from seawater and lithium for tritium production are effectively inexhaustible. The waste is minimal and short-lived compared to fission reactors. There is no risk of meltdowns or runaway chain reactions. If it works, fusion could power civilization for thousands of years. But even then, it will not be a magic wand. Building large-scale reactors takes decades. Rolling them out globally will take even longer. Meanwhile, climate change requires urgent action today, not only in 2050. Fusion is not an immediate fix, but it is a long-term investment in the survival of our civilization. Fusion energy is therefore both reality and dream. The reality is in the labs: superheated plasma, record times, neutron bursts, superconducting coils. The dream is cheap, abundant electricity flowing from fusion power plants across the grid. The truth lies in between. We are moving forward, but slowly. Every new experiment is a step closer to the stars, but the road ahead is long. Perhaps one day, we will look back and say the 21st century was when humanity finally mastered the power of the stars. Today, however, fusion is still more an experiment than a commercial reality. Yet that makes it no less inspiring. It is a story of patience, ambition, and scientific courage, an attempt to replicate on Earth the same process that lights the heavens. Whether it takes 10, 20, or 50 more years, the pursuit of fusion is one of the boldest endeavors humanity has ever attempted. And even if fusion doesn't arrive in time to stop climate change in the next 2 decades, it will still matter. Because if it succeeds, it will matter for centuries, perhaps millennia. It will redefine energy, economics, and geopolitics. It will show that humanity can dream big, invest across generations, and ultimately succeed. So next time you hear that fusion is 20 years away, you might smile remembering the old joke. But you might also realize that for the first time, it may no longer be just a promise. Step by step, we are learning to ignite a small star on Earth. And when that day comes, everything will change. But fusion is not only about physics and engineering, it is also about humanity's vision of the future. Generations of scientists dedicate their lives to experiments whose full benefits may come only long after they are gone. That alone is a remarkable sign of hope, that people can think beyond their own lifetimes, building a foundation for those who will follow. And when the first true fusion power plant finally connects to the grid, it won't just be a technical achievement. It will be a turning point in human history, comparable to landing on the moon or splitting the atom. A moment when a dream that once seemed impossible becomes reality. A moment when humanity can proudly say, "We have captured the power of the stars,